Today we're going to continue with our series, and I have a couple starter problems here for us. The first one says, write the series in summation notation of 7 halves plus 11 fifths plus 15 tenths plus 19 seventeenths plus 26. So I know I'm adding all these, so I start with my sigma, and I have the first term, and I have 1, 2, 3, 4, 5 total terms, so I have the first through the fifth term. Now I need to generate a rule, and again, it is neither arithmetic nor geometric, so I need a separate rule for the numerator and a separate rule for the denominator. So in the numerator, from 7 to 11 is add 4, add 4, add 4, so that would be 4n. 4 times 1 is 4. What do you have to add to it to get to 7? Plus 3, let's check that out. 4 times 2 would be 8, plus 3 is 11. That works. 4 times 3 is 12, plus 3 is 15, so that is working for my numerator. Then in my denominator, it looks like I am adding 3, adding 5, adding 7, adding 9, adding the next odd, so it is a square. So I write n squared. Is 1 squared 2? No. What do you have to add to that to get to 2? 1. Let's try it. 2 squared 4 plus 1, 5. 3 squared is 9 plus 1 is 10. So that is my rule to my series. Then I have one written here in recursive form. So it says S of 8, so I know I am going from the first term to the 8th term. Now I just need to generate the rule. It says first I have a 3, second, third, etc. Then it says take the previous term and add 5. So if I take 3 plus 5, I would get 8. 8 plus 5 will give me 13. So every time I am adding 5 as I move through this series. So that would be 5n. 5 times 1 is 5. Does that get me to my 3? No, I must add a negative 2 to that. Let's see if that works. 5 times 2 is 10, minus 2 is 8. 5 times 3 is 15, minus 2 is 13. So this is my series rule. Now yesterday we ended with some special formulas to calculate series, but there are a few most special ones specifically for arithmetic series, and then there are those for geometric series. And when I talk to you about the arithmetic series, I am talking about a man named Carl Friedrich Gauss. And he is a very amazing mathematician. And part of the reason he is so amazing is he came up with this rule for adding any arithmetic series when he was 9 years old. I'm going to call him Little Freddie, just because I like that name better than Little Carl. Okay? So Little Freddie was sitting in class, and he was one of those very bright students. And many times the very bright students are the most mischievous students as well. So as a 9-year-old, Freddie is in class, and his math teacher knows she has to get this important point across to all the students. And Freddie is just going to ruin the point. So she knows Freddie can get it with no problem, so she gives Freddie another task. She tells Freddie, I need you to add up the first 100 digits. She's thinking, okay, this is going to take him a while. Within 10 minutes, Freddie raises his hand, and he says, well, ma'am, the first 100 digits add up to 5,050. And she said, amazing. How did you get that so fast? What did you do? And he said, well, You told me I needed to add up the first 100 digits. So I knew it would be 1 plus 2 plus 3 plus 4 plus 99 plus 100. So I thought, what if I take this back number and just start adding it to the front number and keep working my way backwards? So that would be 100 plus 99 plus 98 plus 96, plus 97 plus, and I would, when I got to the 50th term, I would have added all the way backwards. So he said, that's 101, 101, 101. And I knew when I got to the 50th one, I'd be repeating myself. So he said, that is 101 50 times. That is 5,050. And she thought, oh my gosh, this child is amazing. And do you know, to this day, anytime we see an arithmetic series, we know we can just think of little Carl Friedrich Gauss as a 9-year-old. So let's see, what did he do? He took the first term plus the last term. So the sum, he took the first term, a sub 1, plus the last term, a sub n, and added those together. And then he knew he'd only have to start adding halfway through because he'd repeat himself. So halfway through, however many he had. And we have how to find the sum of an arithmetic series. First term plus the last term times half as many as you have. And you should easily get the total. So remember the other day, we had this one, 6n, where n equals 1 to 15 of those. This is arithmetic because I am adding 6 every time. So the first term would be 6 plus the 15th term would be 90 times half as many as I started with. That's 15 times 96 divided by half. That's 48 times 15. That's 720. Where yesterday we took n times n plus 1 divided by 2 times 6, and we still get 720. Just a little bit faster way when you recognize it's an arithmetic rule. So let's try a few. It says, find the sum of the first 25 terms. When the first term is 20, and the difference between the terms is negative 2. I always like to draw myself a picture. So I'm starting with 20. Then I'm adding a negative 2, so it'll be 18, 16, etc., down to the 20th term. So here's my picture. Since every time I add 2, add a negative 2, add a negative 2, I recognize that is arithmetic. I should not have been needed to be told that. I should recognize it because I am continually adding the same constant. So this is little Freddie. I am adding up 25 terms. So I take the first term, which is 20, plus the last term. How am I going to figure out this last term? Well, I know to get any term, I take negative 2n. When I do the first term, I put 1 in there, I get a negative 2. Negative 2 plus what gives me 20? Negative 2 plus 22. Let's see if that works for the second one. Negative 2 times 2 is a negative 4 plus 22 is 18. That's working. So this will generate any term. So I'm generating the 20th one. So negative 2 times 20 plus 22 gives me negative 28. So the first term is 20 and the last term is negative 28. Then I have to take half as many as I had. So I totaled up 25 of them and I only need half of that. So this is 25 divided by 2 times a negative 8. This reduces to a negative 4 times 25 is the sum of a negative 100. Let's try another one. Find a sub 15, the 15th term, if you know the arithmetic sum of 15 terms is 255. If you know the arithmetic sum is 255. So I know S of 15 is 255. I also know my first term is 3. So I have 3 all the way to the 15th one. So this sum is 255, so I can put a 255 here, should equal, since it's arithmetic, n, which is 15 of them, halved, times the first term, plus the last term, would be my 15th term. If I double, I get rid of that 2. So that gives me 510 equals 45 plus 15 times a sub 15. Subtract 45. $465 equals 15 times the 15th term. Divide by 15. $31 is the 15th term. Just like there's a rule for an arithmetic series, there's a rule for finding the sum of a geometric series too. And this is by a famous mathematician as well. His name is Archimedes. But there isn't as great of a story behind his, because Archimedes just studied math, and during the time he was studying it, he discovered the rule as a man for a geometric series. And that rule is the sum of however many you're adding up means take the first term times 1 minus the ratio to that many terms divided by 1 minus the ratio. The sum of a geometric series, the first term times 1 minus the ratio to the n divided by 1 minus the ratio. So we'll try a few. Now it says find the sum of the geometric series. However, we shouldn't have had to be told that, because I see it's times a half, times a half, times a half. So it is the series n equals 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, to 10 of them, of 1 half raised to the n minus 1 times 4. So to find the sum of these 10, since it is geometric, I take the first term, which is 4, times 1 minus my ratio was a half, raised to the n, 10 of them, divided by 1 minus a half. Now I do a little simplifying before I punch my calculator. So this would be 4 And this I cannot simplify because I do not know what a half to the 10th is, so I'm just going to leave that for right now. But this one I can. 1 minus a half is a half. Then I can do this. 4 divided by a half. Well, 4 divided by a half is 8 times 1 minus 1/2 to the 10th. Now I punch my calculator. And I get approximately 8, 7.999, etc. Here's another problem. Find the sum of the first 20 terms generated by the sequence 2 times 1/3 to the n. So I have the sum of 1 to 20 of 2 times 1/3 to the n. And that is geometric because I'm multiplying by 1/3. So I would start with the sum of 20 should equal the first term. Well, if I put a 1 in here, it would be 2 times 1/3, which would be 2/3. So my first term is 2/3 times 1 minus my ratio. My ratio was 1/3 to the n. My n is 20 divided by 1 minus 1/3. And again, I do a little arithmetic. 1 minus 1/3 to the 20th I can't do, but this 1 minus 1/3 I can, and that is 2/3. So 2/3 divided by 2/3 is 1. So I get 1 times 1 minus 1/3 to the 20th. Now I pull out my calculator and type in 1 minus 1/3 to the 20th. And again, I get about 1. So do you notice when I keep increasing my power, this seems to subside to 1. And I get whatever is left times my beginning value. That leads us to the sum of an infinite geometric series. These were finite because we had an ending. We had 20 terms. We had 10 terms. But what if I have infinitely many terms? If I have infinitely many terms, this is how you calculate the sum of an infinite geometric series. So if you want to put infinity there, you take your first term and divide it by 1 minus your ratio. We can just eliminate that numerator part of a finite geometric series. And this will only work if our ratio is greater than 1. Because if I don't have a ratio greater than or equal to 1, I have a fraction that's unexplainable here. So in other words, it says the absolute value must be greater than or equal to 1. Excuse me. If it's greater than or equal to 1, there is no sum. I must have decay. If I am continually growing infinitely, I can never find an end to that. But if I am decaying, it just keeps adding just a teeny bit more. So eventually it subsides to 1, which we noticed back here. 1/2 was a decay ratio. 1/3 was a decay ratio. And notice how this part basically subsided to 1. So we cannot have that if this is not decay, because it will not subside. So first, check your ratio. I see this is an infinite sum. Here's my ratio, 0.1. Is 0.1 a ratio of decay? Yes, it is. So I would be able to calculate my infinite sum. It would be the first term. So when I put 1 in here, I get 0. Anything to the 0 is 1 times 2 is 2. So 2 divided by 1 minus my ratio, which is 0.1. That's 2 divided by 0.9. Now, I still don't need my calculator because I cannot have decimals in my fractions, so I have to move this 1 decimal place. So I have to move this 1 decimal place. So that gives me 20 over 9. 20/9 is my sum. Now let's check out the next one. I do see it's infinite. From 12 to 4 is multiplying by 1/3. 4 times 1/3 is giving me 4/3. So it is an infinite geometric. So to find the infinite sum, I take the first term, which was 12, divided by 1 minus the ratio, which is 1/3. That is 12 divided by 2/3. That means 12 times 3/2. That means 18. Now we can apply this infinite sum whenever we have a repeating decimal. So I have a repeating decimal here. I have 2727272727 repeating. So I can apply that infinite sum to this because I know this would be 0.027 would give me this first part. Then to get this, I would have to add 2327. Then to get the next one, I'd have to add another 27, etc. So from term to term to term, I'm adding in 2 more decimal places, so that means multiplying by 1/100th, or 0.01. So it is an infinite geometric series. So to find the sum of an infinite geometric series, I take the first term, which was 0.027, divided by 1 minus my ratio, which meant I added in another 2 decimal places, 0.01, which gives me 0.027 over 0.99. And again, I should be able to move that 3 places. I must move that 3 places. Do you see a 9 in both? 9 goes into 27 3 times. 9 into 990 is 1/10. I can find the fraction using infinite geometric series. Here's another one. I've already got this one written out because I have 4, 5. Took those 2 places, 4, 5, 4, 5, 4, 5. So again, I see it is infinite and it is geometric because I added in 2 decimal places again. So an infinite geometric series, the first term, 0.45, divided by 1 minus the ratio, which was 0.01, equals 0.45. divided by 0.99. Move my decimal 2 places. 45 divided by 99. Again, 9 goes into there, and I get 5/11ths. Now, one last thing. Because we are finding sums, many times in your lifetime you may be asked to invest in an annuity, and an annuity uses a summation rule. To find the value of your annuity after so many years, you take the initial value of your annuity times 1 plus your interest rate raised to the n minus 1 divided by your interest rate. Again, that is the initial amount of your investment times 1 plus the interest rate raised to however many years you're going to keep it there, minus 1, all divided by your interest rate. So let's check out the value of our annuity should we invest $2,000 over 20 years at an interest rate of 8%. So my sum after 20 years of my annuity will be, my initial investment was $2,000 times 1 plus my interest rate is 0.08 raised to the n, which is 20, minus 1 divided by my interest rate of 0.08. Again, I'm going to do a little bit of math. This is 1.08 to the 20th minus 1 divided by 0.08. And again, I'm going to do the 2,000 divided by 0.08. That gives me 25,000 times 1.08 to the 20th minus 1. And now I would punch my calculator, and I get $91,523.93 after 20 years. So annuities are an excellent investment. So let's just review all these rules we're supposed to know. How do you find each term of an arithmetic sequence? The term is equivalent to dn plus c. The difference times whichever place you're at in the sequence plus a constant. The geometric rule is taken a sub n equals the first term times my ratio raised to the n minus 1 power. How we find the sum of an arithmetic series is S sub n will equal half of how many I have times the first term plus the last term. A finite geometric series, S sub n will equal the first term times 1 minus the ratio to the n divided by 1 minus the ratio. And if it is an infinite geometric series, we take this part is eliminated, so it is just the first term divided by 1 minus the ratio. And there should be all your rules to follow you through.